right. These are notes for section 6.3. We are still in chapter 6. We're still talking about probability. It's just a different kind of probability. And I think you're going to find that these are the easiest kind of probability. So we're going to hope that the AP test gives us binomial probability questions. So a binomial distribution is when you have basically two options, either a success or a failure. So you're going to recognize in a given problem either this thing happens or it doesn't. And that will be kind of your clue that, oh, this might be binomial. What you're going to do to check if it's a binomial situation is I've got this acronym BINS. So B stands for binary, which basically means there's two options, so either a success or a failure. The next thing that you're going to want to check for is, oops, I need my pen. The next thing that you're going to want to check for is if your trials are independent. Usually it'll say that in the problem. Other times you can kind of just know that they're independent. So if you're talking about flipping a coin, for example, whatever you get on your first flip has no impact on what you're going to get on your second flip. So you would know that they're independent. N stands for the number of trials. So there has to be a fixed number of trials. And they will tell you in the problem, oh, I'm going to flip a coin 20 times. So then N would be 20. S stands for success. It's actually the probability of success. You will either be told what the probability of success is, or you would be able to figure it out. So if we're flipping a coin, you would know that the probability of a success, let's say a success is flipping a head, then your probability of success would be 1/2 or 0.5. Other times you'll be told what the probability of success is. If all of these four things check out, then you know it's binomial, and then you get to use your calculator to do all of the hard work. Before we get to all the calculator work, if all the bins checks out and you know it's binomial or you're told it's binomial, then you would be able to kind of unlock these two formulas. So if you need to find a mean and a standard deviation, you would do the number of trials times the probability of success. Up here I have labeled N is the number of trials, P is the probability of success. So you would just multiply those two together and you would get your mean. And then you would follow this formula if you needed standard deviation. So again, number of trials times probability of success times 1 minus probability of success. And you'd take the square root and you'd get standard deviation. And again, these only work for binomial. So you would have to already check your bins and make sure that all four of those things check out. Then you can unlock these formulas. All right, so here we're going to kind of go through a little example. So a new board game uses a die to determine how many spaces you move each turn. If you roll a 1, you get a bonus movement card from the pile. Suppose we roll the die 42 times during the course of the whole game. So we're going to kind of check bins and see if this is a binomial scenario. So B would represent binary. So is there a success and fail? Like what would be a success? So a success would be rolling a 1. That would mean that a fail would be rolling a 2, 3, 4, 5, or 6. So if you can discern a success and a fail, that's a good thing. The next thing we need to check for is I, if they are independent. Is each roll of a die independent? Does it matter what happens on the first roll? Is that going to impact what happens on the second roll? No, so they are independent. Then we have to check N. Do we have a set number of trials? Are we rolling this die a set number of times? Yes, we're rolling 42 times. And then the last thing we have to check for is the probability of a success. So what would be the probability of rolling a 1? It would be 1 out of 6. So that would be the probability of success. It remains a constant, 1/6. So bins checks out. That means we get to unlock these two formulas right here. So it's asking how many times would we expect to draw a bonus movement card? Well, when you see that word expect, you should think mean, like expected value. And on the last page, the mean is n times p. And so n is the number of trials, which was 42. And p is the probability of success, which we figured out is 1/6. So you just multiply those two together and you get 7. So we would expect to draw 7 bonus movement cards. Okay. Now, this is going to help us get into how we're going to be using our calculator. This is our big formula for binomial probability. I believe it's on your formula sheet, although you'll kind of have it memorized because you're going to be using it so much. Here's what this formula means. So this is not a fraction. This is what we could call n choose k. So what we're looking for is out of n number of trials, we're trying to find k successes. So this is saying this k is the number of successes that I'm trying to find the probability of happening. This n choose k counts the number of ways that we can have k successes out of n things. So n choose k counts the number of successes I guess I want to rephrase that. The number of ways to have. Here, I'm going to rewrite it. It's just getting sloppy. Okay, start over. So the n choose k counts the number of ways to have k successes in n trials. So it calculates all the different combinations. Then we have this p to the k. P is the probability of success, and k is the number of successes. So basically, p to the k calculates succeeding k number of times. And then 1 minus p, if succeeding is p, then 1 minus p would be failing. And then n minus k, n is the total number of trials, k are the successes. So n minus k would be the other amount of times. So like if you're succeeding k times, then you'd be failing the other amount of times. we're going to go through this formula with numbers, and hopefully it'll make a little bit more sense. But you get to use your calculator a lot. So in your calculator, if you go menu and then you choose statistics, distributions, then you would have to scroll down and you're going to find either a binomial PDF or a binomial CDF. So the difference is if it's a PDF, that stands for a particular number of successes. So you would use that in your calculator when you're trying to find the probability of exactly some number of successes. So whenever there's an equal sign, basically, then you're going to do PDF. That's a particular value. CDF is for a cumulative number of successes. So that would be if you have any kind of inequality. Less than, greater than, in between. Anytime you have an inequality, you're going to be using CDF. PDF is only for an equal sign. So again, here's how you get it in your calculator. Menu 6-5, and then you have to scroll down to either D or E, depending on the problem. Okay, so let's go through an actual example with some numbers, and hopefully that'll make a little bit more sense. All right, so suppose the probability of getting a bullseye playing darts is 0.37. We're going to throw 25 darts, and we're going to count the number of bullseyes. Each throw is independent. So we need to go through and just check bins and give full evidence. So the first thing is B. Do we have a success and do we have a fail? What would be considered a success? Well, we're counting the number of bullseyes. So a bullseye would be a success, and then anything that's not a bullseye would be a failure. So B checks out. I in bins is for independent, and we were told they're independent, so that checks out. N is for the number of trials, so were we told how many times we're going to throw the darts? Yep, it says we're throwing 25 times, so N is a set number of trials. And then S in bins stands for the probability of success. So do we know what the probability of getting a bullseye is? Yep, right here they told us that the probability of getting a bullseye is 0.37. So that's the probability of a success. So bins checks out. So this is definitely binomial. So then we can unlock any of these formulas. So we can unlock that formula or these two formulas. All right, so in this question, it's asking how many bullseyes would we expect to get? So anytime you see the word expect, think expected value, which is the mean, and the formula is N times P. So N is the number of trials. So in this case, we're throwing 25 times. P is the probability of success, which we found was 0.37. We were told that actually. So do 25 times 0.37 and you get 9.25. So we expect to get 9.25 bullseyes in 25 throws. On average, we should say. Okay. All right, now we're going to find the probability that we get 12 bullseyes. So we're throwing 25 times. We're trying to find the probability that we get 12. So that would be the probability of exactly 12, equal to 12. So when it's an equals, we're going to use PDF in our calculator. But we do need to show the setup of this formula. You always have to show the setup of the formula, but then you're going to use your calculator to speed things up. So N is the number of trials, so in this case it's 25. K is the number of successes we want. So going back here, the number of trials is 25. We want 12 successes. So that's 25, choose 12. Next in the formula is P. That's the probability of success. And it's going to get raised to K, which again is the same as right here, the number of successes we're hoping for. So probability of success raised to the number of successes we're hoping for. The probability of a success was 0.37. We raised that to the same number as down here, the number of successes we're trying to get. And then in the formula, we have 1 minus P. So it would be 1 minus 0.37. And then that's going to be to the N minus K. Here's your N and K. Basically, you just do top number minus bottom number. So that'll be 25 minus 12. Okay, so now for typing this into the calculator, there is a way to type and get 25, choose 12, and then multiply it by all of these things. But it's a little cumbersome, so there's a faster way that we can do this in our calculator. So I'm getting my calculator loaded up here, and I'll show you. And again, we're doing equals 12, so this is going to be binomial PDF. And by the way, we don't ever write down our calculator steps. The AP people don't care, and they don't want to see that. That's why you got to write out the formula. Okay, so we're going to go menu 5, which is probability, then down to 5, which is distributions, and then we're going to arrow down until we see binomial PDF or binomial CDF. So we want PDF. Okay, so the number of trials, how many times were we throwing the darts? The number of trials was 25. So you're going to put a 25 in there. The probability of success, remember that was 0.37. The probability of getting a bullseye was 0.37. And then the X value, how many successes are we trying for? We're trying for 12 successes. You see where X equals 12. So 12 goes in here. And then we're going to hit OK. And then this is our answer right here, 0.84. All right, so I don't write down any of my calculator steps. I write down the formula, then I go to my calculator and I get the answer. As I was using my calculator, I noticed something. Here it says menu 6.5. For some reason, didn't I do menu 5.5? Let me look again. Menu. Oh, I guess I can get there either way, huh? Oh yeah, I can get it that way, or I can go menu 6.5 and then get it there as well. So there's a couple different ways you can get it, but I'll try to follow what I said, menu 6.5, just so we don't get confused. All right, so we're still in the same scenario, the throwing the darts. This time we're going to find the probability that we get less than 10 bullseyes. So if I write that out with symbols, I'm finding the probability that X is less than 10. Okay, so we need to follow this formula, but we have to modify it a little bit because this formula, exactly as it's written, is when there's an equal sign. We have an inequality now. So we have to kind of string together several of these. So here's what I mean. If we are finding the probability of less than 10 bullseyes, that means that we would be starting with 0 bullseyes and then finding the probability of 1 bullseye and then finding the probability of 2 bullseyes and so on. So when we set up our formula, again at the top is the total number of trials. Here we would start with 0 successes. The probability of success was 0.37. We raise that to the number of successes. Then we do 1 minus 0.37, which is so if we do 1 minus 0.37, we get 0.63. And then we raise that to the n minus k, so 25 minus 0, which would be 25. So this is basically succeeding 0 times, failing all 25 times. The next one would be 25, choose 1. So this is the probability of no bullseyes. This is going to be the probability of 1 bullseye. So to be 0.37 to the 1, this exponent matches that bottom number. And then it would be 0.63, and then n minus k, so 25 minus 1. We get 24. This would continue going on, because if we want less than 10, that's from 0 all the way up to what? Strictly less than 10 means that our highest would be a 9. So then this would be 0.37 to the 9th, and then this would be 0.63 to the 25 minus 9. Okay, so again, this would be our starting and this would be our ending, because less than 10 goes from 0 to 9. All right, now we would not want to type all of this in our calculator. That would take so long. But you do need to show this amount of work. So the AP people want to see the beginning. They want to see the next one to establish a pattern. And then you can do plus ... plus the last one. You don't have to write all 0 through 9 out. But now is where you're going to go to your calculator. So we're going to go menu, 6, 5, and then you're going to go down and then decide, is it PDF or CDF? Well, since this was an inequality, less than 10, we're going to do CDF. Number of trials was 25, because we were throwing the darts 25 times. The probability of success is still 0.37. But now we have an option for a lower bound and an upper bound. That is what these numbers are. So your lower bound would be 0 and your upper bound would be 9. Because again, if we're less than 10, strictly less than 10, it's going from 0 to 9. And then hit OK, and there's your answer, 0.548. But you got to show the setup, and then you can use your calculator to get the answer. All right, for part B, what's the probability we get at least 13, but less than 20? So, at least 13. At least 13 means 13 or more. And then less than 20. So this would be in symbols, what this is saying in words. All right, so we start our lower bound would be 13 because it can equal 13. Our probability of success is 0.37. Raise that to the same power as what this bottom number is. 1 minus 0.37, we already found was 0.63. And then this exponent will be 25 minus 13. So 12. Plus, the next one would be 25, choose 14. 0.37 to the 14. 0.63 to the 25 minus 14. Which would be 11. Plus, dot, 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 plus the last one, 25. Now, what would be the upper bound? Be careful. It's got to be strictly less than 20. So the highest it'll go is 19. And then it'll be 0.37 to the 19. I'm running out of room. 0.63 to the, what's 25 minus 19? 6. All right, so that's the setup you show. But now you get to use your calculator because we do not want to type all that in. Just be aware, though, that the lower bound was 13, the upper bound is 19. It can equal 13, but it cannot go all the way up to 20. So 19 is the highest. Okay, so again, because we've got inequality symbols, we're going to do binomial CDF in the calculator. So we're going to do menu 6, 5, arrow down to binomial CDF. The number of trials was 25. The probability of success was 0.37. This time the lower bound was 13 and the upper bound was 19. And then you hit OK and you get 0.0907. Okay, next example. What's the probability that we get more than 8 bullseyes? So more than 8, greater than 8. All right, so the first one, if we're strictly greater than 8, then what would be our lowest number? It would be a 9. 0.37 to the 9th, again, that exponent is the same as whatever this bottom number is. 1 minus 0.37 is 0.63, and that will get raised to the 25 minus 9. 16. And then we've got the next one. So we're starting at 9 and we're going up, greater than. So the next one would be a 10. That would be 0.37 to the 10th. 0.63 to the 25 minus 10. Plus, dot, 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 plus. What would be the highest this thing goes? If we're going greater than 8 and we're only throwing the darts 25 times, the highest would be 25. So then it would be 0.37 to the 25th, and it would be 0.63 to the 25 minus 25, which is 0. So on this one, the lower bound is 9 and the upper bound is 25. So again, because it's an inequality, we're going to do binomial CDF. So menu 6, 5, binomial CDF. Number of trials is 25. Probability of success is 0.37. The lower bound was 9 and the upper bound was 25. Because we're only throwing it 25 times. That's the highest it's going to go. So 0.6152. All right, so just to clarify, You have to show the first, the next, and then dot, 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 the last. Anytime it's an inequality problem. If it's an equals problem like this one, you only have one thing, one chunk to write. And again, if it's an equals, this is a binomial PDF when it's an equals sign. And then anytime it's an inequality, we do CDF. Okay. So that's where we're going to stop. So always check bins. Anytime you think that there's a success or a fail, check that. Check if they're independent. Check if there's a set number of trials. Find the probability of success. As long as bins checks out, you get to unlock these formulas for mean and standard deviation, and then you also get to unlock this formula. Okay? And you have to show your setup, but then you can go to your calculator to get your actual answer. All right, so that is 6.3, day 1. Now you can work on the homework. Have a good weekend. I'll see you Monday.